So it's a pleasure to welcome you all to our second installment of Logical Perspectives Open Lecture. The first one was took place 2 years ago during a COVID time, and which was a rather successful event for everyone. So we decided to repeat it one more time here, and I'm very grateful to our two esteemed speakers today who agreed to come and to deliver the lectures. In these times of trouble where not everyone is ready to give such lectures. So our first speaker is Professor Johann Makowsky, who is Professor Emeritus of Technion in Haifa, Israel. He was born in 1948 in Budapest, Hungary, and then studied in famous ETH institution in Zurich, Switzerland. And he's well known for his fundamental contributions to model theory in computer science and computer science logic in general. So the topics that were prominent in his research are, I would say, database theory, logic programming, algorithms, graph algorithms, finite model theory, and other topics. He was also a very significant figure in the field of organization of logic in computer science community, one of the founders of European Association for Computer Science Logic, Ackermann Award, and in general, his contributions to our field, to the field of logic in general, are very significant. So I asked his longtime student and collaborator, Dr. Elena Rave, to record some introductory words about Professor Makowsky, which I will now demonstrate. So, share screen.
Dear friends and colleagues, my name is Elena Rave. It is my great pleasure and honor to introduce Professor Makowsky's lecture. When I was entrusted with this task, I approached it as a responsible person, and I started preparing an outline of my speech. So I stumbled at the very first sentence. So I want to introduce and what is epithet can I use to describe the 30 years of my communication with Janusz? What is he for me? A mentor? Sure he is. But this does not encompass all the roles he has played in my life. Clearly, for all his master and PhD students, Janusz is a teacher in the widest sense of the word, professional, academic, and ethics. He stays in touch with his ex-students for years, helping us in every possible way. But this is just one side of his incredible talents. So, what is he for me? Also a friend? By friendships presupposed equality, and Janusz is a person with the scope of a Renaissance personality. I am not going to enumerate his achievements in science. Everyone uses the internet and can easily find his research records. Janusz also a writer with whose deep knowledge in literature is not easy to match. He is a musician with subtle understanding of different music genres. He is also a cook and a gardener and many other things. So what is Janusz for me? After these 30 years of intense communication, like some of his other ex-students, I feel I am a member of his family. At least I hope I am. After this lengthy deliberation, I think I know how I want to introduce Professor Janusz Makowsky. So, it is my great pleasure and my honor to introduce a man of the world, one of those whose role is to educate the young and make this world move forward. He is an internationally known mathematician who has trained and cultivated a taste for science in several generations of researchers. Professor Janusz Makowsky. He will share with us his travels in logic, computer science, and mathematics through his 50 years of research. Thank you very much for your attention.
Okay, well, thank you very, very much for this invitation. I will lead you through my whole research career and some new things, and possibly teach you some lessons I've been taught on the way. This is a new version of a talk I've given as my retirement address, and it's updated. So we go through from mathematical logic, categoricity, to abstract model theory, and then to model theory, computer science, and we will then go to my further developments in combinatorics and graph polynomials, and depending on where we are, we will hear the last lessons, depending on how much time you give me.
But you haven't yet shared the slides with us. We see your screen.
Huh?
We can
I've
see your
shared the
screen, but
slides.
not the slides. So you have to probably share a different window.
Okay, so try again. Here. Now you can see it?
Yeah, yeah, very good.
Okay. So in the good old times in the 70s, logic was considered as the foundations of computability theory, but nobody really wanted to have logic as a part of, or computer science as part of logic. There was heavy resistance from the electroengineering and computer science communities. There was also resistance from the Association of Symbolic Logic, and especially the German Association of Logic, and also on departmental level. Now, logic traditionally was divided into computability theory, model theory, proof theory, and set theory, and non-standard logics and other things. But computability led to complexity theory, model theory led to automata theory, finite model theory, verification, proof theory led to automatic theorem proving, etc. And set theory became part of the modeling tools for data structures. Now, when I started to study in Zurich, my supervisor was Specker and Hans Leuchli, and we were in the seminar where Mr. Bernays, over 80, was still actively participating in the seminar. And in one of those seminars, when I was in the 5th semester, we decided to read Morley's fundamental paper on categoricity. So categoricity was a topic which was introduced simultaneously almost by Rilnaczewski in Poland, by Svenonius in, I think, Sweden, and Erwin Engeler in Zurich or Berkeley at that time. And they characterized independently Aleph-0 categorical theories. Now, the tools and developments which led to Aleph-1 categoricity were developed by Ehrenfeucht, Mostovsky, and Bob Watt. So Ehrenfeucht and Mostovsky studied models with large automorphisms using Ramsey theory, and Robert Watt, together with Morley, applied this to categoricity. And in 1965, Morley's famous paper appeared, which proved that the theory, a countable theory, is kappa categorical for some uncountable kappa, if and only if it is kappa categorical for every uncountable kappa. Now, this is a landmark paper which really got model theory in the modern sense started. And its most important part, besides the theorem, was a list of open questions. So Morley asks, among other things, is there a finite axiomatizable first order theory which is kappa categorical for all kappa or for all uncountable kappa? And attacking these questions required understanding of the structure theory of kappa categorical theories and some idea on how to prove or disprove finite axiomatizability. At the time, to prove non-finite axiomatizability, one could use Ehrenfeucht-Frey games, ultra products, or maybe some other methods, but Ehrenfeucht-Frey games seemed to me the most promising thing to do. So I was lucky because already in the 7th semester, I managed to prove a theorem. And actually, because I went to a logic conference in 1970, and I met Alistair Lachlan, and he asked me what I was doing. And then he handed me over a preprint of his and Baldwin, which I should use for what I had in mind. And indeed, I managed to prove 3 parts of a theorem. The first order theory, which is Aleph 0 categorical and strongly minimal, which is a special case of Aleph categoricity, cannot be finitely axiomatizable. Then I showed there is finitely many axiomatizable complete first order theories which are superstable. And if there is an infinite finitely presentable group with only finitely many conjugacy classes, then I can also construct a finitely axiomatizable Aleph 1 categorical theories. Now, the most remarkable thing about this is that the group theory problem, the if of the group theory section, is still an open problem listed in a famous paper about open problems in group theory. Now, the first lesson I had to learn was the following. In the 2nd edition of Chang and Kiesler's model theory credits me for partially solving 2 of Morley's square problems. And at the time, joint papers were not common practice, at least not in German-speaking countries. And Hans Leuchli let me publish the results under my name alone. In Chang Kiesler, credit is not extended to Leuchli, although I clearly stated his role in the results. Besides Ehrenfeucht-Frey games, I also used non-periodic tilings of the plane, an idea which was suggested to me by my supervisor Leuchli, whose work is also not credited usually on this. This is overtaken by the big noise which Penrose is doing about Penrose tilings. So I soon realized that although I got my master thesis for this and I got a nice publication, that this was all I could prove using the available tools. And in the 71 Logic Colloquium in Cambridge, I met finally Schelach and I met Viktor Marek, and both of these encounters had a major impact on my further research. Most of Morley's problems were actually solved by Saharon Schelach. Just the finite axiomatizability question really withstood his attacks. Now, the solutions to the problems came about later. First, M. Peretyatkin showed that there is a finitely axiomatizable omega 1 categorical theory. And then Boris Silber and later with different methods, Cherlin, Harrington, and Lachlan solved the general problem. Cherlin, Harrington, and Lachlan used some results from classification theory of finite groups, and Boris uses some results on Diophantine equations at the time. To overcome the difficulties I had not been able to overcome. But indeed, when I stopped working on this problem, neither of the results on Diophantine equations or on finite groups were available. So here are the heroes of the finite axiomatizability theorem: Boris, Greg, Leo, and Alistair. I couldn't find the picture of Peretyatkin on the internet. So the next lesson I learned on this is search and read a lot of the literature, even if it goes far back. And today I would add there is mathematics from before the internet. And the second one is go to conferences already as a student, but be properly prepared. Because when I came to the conference, I was prepared to being asked, what are you working on by now? Now, at this 71 conference, it was Victor Marek who introduced me enthusiastically to Lindström's theorem, which has been rediscovered by Harvey Friedman, who gave it much publicity. So what a great theorem this is. Predicate logic can be characterized among all the logics as the only one which satisfies the Löwenheim-Skolem property and one of the following compactness or axiomatizability. Now, among all the logics has to be specified. This is with standard first-order logic semantics and extensions of first-order logic in the standard sense. But the important thing here is not maybe also the proof, but even more important, that it created a new paradigm. You could try to study logics as a space of all logics and characterize them within this space. The result by Lindström was preceded by work on generalized quantifiers, and I immediately studied Lindström's papers and what was known about first-order logic and prepared a seminar talk in Zurich about it. Later, Lindström told me that his original motivation for the theorem had been to find a new application of Ehrenfeucht-Frey games. The rest was a kind of a lucky coincidence. So here they are again, Ehrenfeucht-Frey games. I spent 72 partially in Warsaw as an exchange student, working under the late Andrzej Mostowski on generalized quantifiers. There are two ways of studying extensions of first-order logic. One is via generalized quantifiers, and the other one is via fragments of infinitary logic. For instance, Barweis had shown that the admissible fragments of L omega 1 omega satisfy the Craig interpolation theorem. And in a different line, Dana Scott and independently Erwin Engler had shown that all countable structures over a countable vocabulary can be characterized up to isomorphism by extensions in L omega 1 omega. So in this time when I was working on this, I had the luck to meet George Kreisel, introduced by Bernays, and I told him what I tried to do. I wanted to find a characterization of logics using the other properties than Löwenheim-Skolem, Tarski theorem, and compactness. So Kreisel suggested in his own criteria of choosing, Kreisel suggested his own criteria of choosing logics in a 68 paper, the choice of infinitary languages. And so after I talked to him about this, I told Kreisel about my ideas, and we had some intensive correspondence later on. He also provided me, in my first encounter with him, after I told him about this, a preprint of Leslie Tarp without telling me that he was referring it before it was accepted for publication. So I naively used the material in my PhD thesis, trusting that it was given to me in good faith for use. I generalized Tarp's definition and proved innocently theorems which may have been also on Tarp's mind. In spring 73, Kreisel sent me a telegram offering me a position at Stanford. In searching recently in the archives, I found a recommendation letter of Kreisel he had written for me, but that's besides the point. So the next lesson I learned is, do not circulate papers you are supposed to treat confidentially. Kreisel helped me by pointing out Tarp's result, but he did this in an unethical manner. So my next attempt was to get involved with Craig's interpolation theorem. And so you probably know, so it says if you have two vocabularies, one containing both containing only relation symbols R, and you have an implication phi RS implies psi ST, then there is an interpolant which doesn't use the extra predicates and only uses the common vocabulary. So using this, I proved let L be a logic such that Craig's interpolation theorem holds for the logic, and such that all countable structures over a countable vocabulary can be characterized up to isomorphisms. Then L omega 1 omega happens to be a sublogic of this logic. Now, this was a proof which was inspired by Solomon Pfefferman's work, among other things. So Pfefferman-Watt theorem already started to enter into my toolbox at this time. So here is a formulation of the Pfefferman-Watt theorem. It says if you have two structures and you form a composition like A disjoint union B, then you can find a reduction sequence of formulas and a Boolean function such that you can test individually whether something holds in A or whether something holds in B. And this theorem was extended by Leuchli and independently by Schelach to monadic second-order logic and has become a very important tool in finite model theory. So here is a picture was taken from me with Pfefferman just shortly before he died. Now, in 1973, I also announced the characterization of minimal fragments of L omega man, which satisfy the Suslin-Kleene version of the interpolation theorem and characterize one countable structure up to isomorphism. And the same result was announced in the notices of the AMS, also by Harvey Friedman. Now, it turned out that I actually used tools which I didn't completely master at the time. But however, because Friedman announced that he had been proving the same theorem, this brushed away my gut feelings, and it made me believe that I had used the tools correctly. Only when I lectured at the Stanford Logic Seminar in '73, Jonathan Stabby showed me a counterexample to my and Friedman's theorem. Together, we fixed the theorem which had led to my prolonged collaboration with Schelach in abstract model theory. The most important lesson here is, do not trust your own hand waving. Do trust your gut feelings when something is wrong with your proof. So the recurrent themes of my work so far were Ehrenfeucht-Frey games, reduction theorems, interpolation theorems, and abstract model theory. But abstract model theory became rather set theoretic and technical. Until '84, much of my published work remained in abstract model theory, and it culminated in 3 chapters in the book Model Theoretic Logics, edited by Barweis and Pfefferman in '85, where I contributed 2 and co-authored the 3rd chapter. But after its publication, the philosophy reminded, including Lindström himself, lost interest in abstract model theory. Among other reasons, my theorem with Schelach had introduced large cardinals into the field, spoiling the hope for aesthetically neat theorems. Since '76, I had also worked with Schelach on generalizing the Morley categoricity theorem, and I supervised my Japanese student Sakae Fuchino on this topic. I finished our joint work in '82, and it was published on Schelach's suggestion by me alone in the handbook just mentioned before. And then I changed my research topic to computer science. However, this chapter 20 in this book actually is the basis of abstract elementary classes, further pursued, among others, by Baldwin, Boney, Grossberg, Mackay, Schelach, Van Dieren, and Andres Villasetes, and maybe others. Now, Shelach taught me two lessons. Never let aesthetics or ideology prevent you from proving a theorem, and also not everybody who asks a mathematical question is willing to hear the answer if it requires too much time, energy, or skill to understand it. Now, actually, lesson 6 is what he learned, and lesson 5 is what he concluded from this, that you shouldn't ask, is it worth proving a theorem? Would it nice if the following is true? He said, first prove it, and then discuss whatever you want to discuss. Well, between 75 and 80, I was working in Berlin and in Israel at the Hebrew University. In Israel, because I was collaborating with Shelach and increasingly with other Israeli logicians, mathematicians, and emerging computer scientists. And also I got married to an Israeli. This had major impact on my career planning. I planned to move to Israeli academia. And so to do this, I was advised to embrace logic and its potential impact on computer science. I should thank here to Saron Shelach, Eli Shamir, and Katriel Berry, Shimon Evan, Amir Pnueli, and Dov Kabai for their support in finding me a job in Israel. My background in theoretical computer science actually did start in Zurich, and I was aware of the connections. I had attended at Specker Straßen seminar in Zurich in the early 70s, where we studied evolving complexity theory. I had attended Engeler seminar in Zurich, where we studied how to use computers in combinatorial group theory. And it was finally Eli Shamir in Jerusalem who gave me the crucial impulse to approach computer science successfully. In 78, he arranged for a blind date with Katriel Berry, who was struggling to find the right definitions of database dependencies. He also told me to attend the ACM Stock Conference in 79 in Atlanta, where I got acquainted with Warren Pratt and his dynamic logic. So how is your model theory used in computer science? I tried to identify problems in theoretical computer science which could be tackled using model theoretic methods. I was looking for model theoretic characterizations of certain classes of syntactically defined formulas for analogs of Lindström's theorem. At a logic colloquium in 82 in Florence, I was invited speaker and I gave a talk on model theoretic issues in theoretical computer science, relational databases, and abstract data types. Yuri Gurevich discussed this paper with me at great length in the years 82 to 84, and it inspired him to write his paper, Logic and the Challenge of Computer Science. But I had written my paper for the wrong audience. The logicians were not interested in computer science, and the first LIX conference was held in 86, the first CSL conference was held in 87, and EACCL was founded in 92. So lessons on changing topics. When you change fields, do not leave your old toolbox behind. But one can be too early and in the wrong place at the same time. Lesson 9, show your results personally at the relevant conferences. People don't read if they didn't hear about you talking. So my time and work in logic and computer science divides in two parts. From 80 to 95, I mostly worked on the foundation of database theory and logic programming. With Katriel Berry, I established the beginning of the theory of database dependencies. Our work was continued in the PhD thesis of Moshe Bardi. With my students, Viktor Markovits and Udi Rotic, I established the B-interpretability of two competing data models, the relational model and the entity relationship model. And together with my student Elena Rave, we analyzed normal forms on database design. I also tried my hands in descriptive complexity, inspired by work of Moshe Bardi and Neil Immerman. With my student Lena, we tried further applications of model theory to database design, but Jeff Ullman had declared database design at that end. So actually at the conferences, papers in this direction were usually not accepted anymore. We succeeded in explaining Boyce code normal form, but had no impact. We succeeded in applying reduction theorem like Pfefferman-Woth theorems, but had no killing applications. But just in the last 5 years, with significant growth of computing abilities and resources in data centers, application of Pfefferman-Woth-like theorems have become feasible and used. On logic programming, I worked with Bernd Marr and Alon Ittai, and we worked out about why Horn formulas are so central for logic programming. Together with Mulis Sagiv, we studied the role of side effects in Prolog, and later with Eldar Fischer and Lena Rave, we also worked on the complexity of SAT for formulas of bounded click width. Summary, I was only interested in the logical foundations of computer science. I rarely attended conferences in these fields, so recognition for my work came late, but it did come. By 1995, I was ready to change fields again. In the 90s, 2 students were about to change my research dramatically. My former MSc student, Udi Rotic, returned from his experience in industry. He wanted to work for a PhD in graph algorithms, but as he insisted, without involving logic. He proposed to extend the notion of tree-width of class of graphs as a graph parameter in the use of fixed parameter tractability. Finally, using logic, in spite of his wish, we came up with a notion of roughly equivalent to click width introduced by Bruno Courcelle and Ola Reu. This led to an intensive collaboration with Bruno Courcelle. So model theory finally had its use, the Pfefferman-Woth theorem and transduction. In my paper, Algorithmic Use of Pfefferman-Woth theorems, which I presented originally for the 100th birthday of Tarski, I surveyed how one could use it in finite model theory and presented new results. With my student, Udi Rotic and Courcelle, we extended and laid the foundation for other width parameters. In 1996, I started to supervise an immigrant student from the former USSR, Gregory Kogan, who wanted to work on the complexity of computing the permanent. He came with impressive letters of recommendations. He had some spectacular partial results for matrices over a field of characteristics 3. He was a virtuoso in combinatorial linear algebra, and unfortunately, he dropped out before finishing his PhD. Now, computing permanence actually had been on my mind already long ago, but I didn't have a chance to get into it really. I came across first at Specker's 60th birthday conference in 1980. There, Valiant presented the complexity classes VP and VNP, and the permanent of a matrix is given by an expression which is a multivariate polynomial. Computing the permanent of a 0-1 matrix is hard. It is Sharpe complete in the Turing model computation, and it is VNP complete in Valiant's algebraic model of computation. So people started to look at special cases of matrices, and inspired by what I had done on graph theory and Courcelle's theorem, I proved a theorem which actually is orthogonal, but in similar style as Barvinok's theorem of 96. Let M be the set of real matrices of rank R. Then for every AM, there is a polynomial time algorithm AR, which computes permanent of A. Actually, the quantifiers are wrong. There is a polynomial time algorithm such that for every matrix, this can be done. Now, I did the same let T be the set of identity matrices of graphs of 3 with at most n, then again there is a polynomial time algorithm such that for every such matrix, it computes the permanent of A. The two theorems are incomparable, but I was inspired by Kogan's preliminary work because I was challenged and I wanted to prove a theorem which Kogan couldn't prove. However, I realized that my theorem had nothing to do with permanence. It was much more general and really worked under some logical restrictions quite generally for polynomials in indeterminates given by the entry of the matrix. Alas, I had no clue how to find spectacular examples. So during a sabbatical at ETH in Zurich, I met Vladimir Turayev and showed him my theorem. He looked at it, and after a while he suggested I should try to apply my same techniques to the Jones polynomial from knot theory. Well, but I had no idea about Jones polynomials and about knot theory. So I studied knot theory intensively for a few months. After quite an effort, I managed to prove a theorem. Assume K is a knot with a knot diagram dk of 3 with K, then the Jones polynomial is fixed parameter tractable with parameter K. However, the proof seemed to work for other graph polynomials as well. Among them, the Tat polynomial, chromatic polynomial, matching polynomial. But these were special cases. So how could one find infinitely many examples for which one could apply the theorem? So here comes the second relevant encounter. In 2005, while attending CSL in Oxford, I paid visit to Boris Silber, whom I knew and had met before due to our work on Morley's problem on finite axiomatizability. Boris had never heard of graph polynomials. So he asked, what is this about? I gave him examples, Tat polynomial, chromatic polynomial, matching polynomial, but in each of them, he immediately or almost immediately saw them as examples which are interpretable in some Aleph 0, but not Aleph 1, in some Aleph 1, but not Aleph 0 categorical theories, sorry. We spent the next days together producing generalizations of chromatic polynomials, which I later called Harari polynomials. So for the last 20 years, I was studying graph polynomials. Graph polynomials can be studied to obtain information on graphs, like evaluations of the Tat polynomial encode many graph invariants, or graph polynomials can be studied as polynomials which, instead of numbers, are indexed by graphs. Example, the acyclic matching polynomials of past cycles, complete graphs and complete bipartite graphs are respectively the Chebyshev polynomials of second or first kind, Hermite polynomials and Laguerre polynomials respectively. And you can, in the first line, two graph polynomials have the same distinctive power if they distinguish between the same graphs. Now, the two approaches to graph polynomials are quite different. The first case really tries to do graph theory, and the second case just tries to identify families of orthogonal polynomials. But with my collaborators, we have managed to create a new field in graph theory with 2 Dagstuhl seminars, 2 special sessions IAMS meetings, and 1 CM mini symposium. In 2009, I organized with Martin Grohe a special session, Model Theoretic Methods in Finite Combinatorics. In 2014, I organized with Elise Moanagan, Andrew Goodall, CM conference towards graph polynomials at general theory. And in just this year, we finally held the conference planned 2 years ago, graph polynomials and matroid polynomials towards a comparative theory organized by Emmerich John, myself, and James Oxley. We also had 2 Dagstuhl seminars in 2016 and in 2019 on graph polynomials and comparative theory. And the second one, I couldn't be a co-organizer because of the rules of Dagstuhl that head organizer should, or one of the organizers should change.
Mhm.
Now, unifying theory of graph polynomials, I had several students working on this. Ilya Averbuch and Benny Godlin and Tomer Kotek Averbuch and Kotek wrote a brilliant PhD thesis. Benny Godlin wrote several papers with us, but he dropped out of a PhD program and joined industry at some point. Lena Rave, Udi Rotic, and Kogan had worked with us and influenced us and published papers on the field as well. My other co-authors in the field were Mickey Herman, Andrew Budol, Stephen Noble, Boris Silber, Orly Herskovitzy, Eldar Fischer, and Ruja Shan. And finally also Bruno Kursel, Markus Bläser, and Holger Dell. Now, so this is where I stand with my own work, and it still continues, but I would like now to tell you a few words about how I see that model theory has impact on combinatorics and finite model theory. Now, the classical first stage of finite model theory was mostly concerned with the difference between finite and infinite model theory, like compactness and completeness fail, preservation theorems fail, descriptive complexity theory, like capturing complexity classes below P space or sharp P, and also 0-1 laws. Now, in more recent developments, the notion of width of finite structures has been a very important property in analyzing algorithmic graph theory and similar things, and they've established algorithmic meta-theorems. Bruno Kursel initiated and developed single-handedly the model theory of monadic second-order logic and on graphs, and this led to the study of various notions of width of finite structure and its algorithmic consequences, and to the rediscovery of the Specker-Blatter theorem on counting labeled structures. Now, in the last 10 years, there is quite an exciting development where the width of finite structure meets classical stability theory. In recent work, Isolde Adler, Neshetril, Osana Demandes, and Sieberts led to the discovery of connections between classical stability theory and sparsity of finite structures. Now, there are many, many papers, but if you want to get into it, here are 3 links, which I highly recommend. One is the 2012 book by Neshetril and Osana Demandes, Sparsity, Graphs, Structures, and Algorithms, and a very recent paper by Neshetril, Mendes, Rabinovich, and Sieberts, Linear rank width meets stability, and even more recent paper by Braunfeld, Neshetril, De Mendes, and Sieberts, decomposition horizons from graph sparsity to model theoretic dividing lines. Now, this is not computer science anymore, but this is a rapprochement of classical model theory with recent developments on finite model theory, which I find very exciting. And if I had been younger, I would work in this more intensively, and I would try to supervise students in this direction as well. Another exciting development in the same style is model theory and the speed of hereditary classes of finite structures. So here we look at the following problem. Let C be a class of purely relational structures of a finite vocabulary with finitely many relation symbols R bar. And if C is hereditary or monotone, this function below will be called the speed. So we define S as for Specker in my case, C of n is the number of ways you can equip a labeled n element set with relations R such that the resulting instructions happens to be in C. Now the Specker-Blatter theorem and its generalizations analyzes the behavior of this function modulo M using model theory and combinatorics. Well, you can read about it in our most recent paper, and the references there, extensions and limits of the Specker-Blatter theorem, which we just posted a few months ago on the archive. Now, the same function SF, but restricted to hereditary classes, was studied by Makowsky and Terry using the model theoretic notion of mutual algebraicity. Now, this is algebraic types are used in Morley's paper originally, and Makowsky's extended this to a notion of mutual algebraicity, and he used this notion to deepen the analysis of the speed function, which was initiated by Bolobash and his collaborators. And here is a recent paper you can look at, jumps in speed of hereditary properties in finite relational languages, which was just published this year in the Journal of Combinatorial Theory, Series B. Now, we won't have time further, but here is another link which puts, shows interplay between these fields. Connection matrices, graph limits, and flag algebras. Well, flag algebras were initiated by Rasborov, and connection matrices and graph limits were introduced by Latsilovas and many of his collaborators. There is quite a bit of interplay indeed between finite model theory, connection matrices, graph limits, graph polynomials, flag algebras, and extremal combinatorics. And again, if I was younger and not yet retired, I would also try to supervise students in this direction, which I find indeed most promising. Now, this almost ends my tour through my own work and future developments. I would like to thank here, but if time permits, I will show you a few more of the lessons I learned on the way. So I was lucky in receiving advice by and learning from my teachers Specker and Leuchli, and not mentioned previously Benno Ekman and Christian Blatter, who were Ekman taught me algebraic topology and algebra in Zurich, and Christian Blatter taught me modern style real function theory. And indirectly, they were not formally my teachers. I learned a lot from Bernays and Engeler in the seminars and by Andrzej Mostovski while I was visiting Warsaw, and from George Kreis, whom I met and corresponded with. Then I learned a lot of my graduate students and of my many co-authors, but I would like to thank especially Viktor Marek, Vladimir Turayev, and Boris Silber for their suggestions, which made me change my research directions. And also thanks here to the organizer and the audience. Now, as described in great length, my experience in moving from mathematical logic proper to using logic in the foundations of computer science and combinatorics in the proceedings, in this talk, sorry. I formulated a few lessons one can learn from my experience casually as they come along with my narrative. Others have written such lessons and inspired me. My favorite is a paper by Giancarlo Rota, 10 Lessons I Wish I Had Been Taught, which was published in '97 in the notices of the AMS. Now I'll pick more of the lessons I have learned in my career, which I would like to tell to younger researchers. Now, The first one concerns pitfalls of memory and credit. A bit of introspection always helps. How did I choose my particular topic? Was I inspired by somebody's talk? With whom did I talk about my work and when? Did I quote all relevant papers? I found out that actually I had heard a lecture by John Barwise at one of the conferences, and I even had notes in my notebook, but completely forgotten about it, and later picked up the same topic and completely forgot. I only discovered much later that actually I had heard this talk of his. So one has to be very careful, and it never hurts of being generous with credit. Now, here is another advice I learned from Yuri Gurevich: don't compete, be inspired. And this came about like this. I once started a paper with X and Y proved the statement A. We now prove a stronger result, namely B. Now, Yuri wrote to me, why are you so competitive? I did not think I was. I asked how he would have written it. And he answered, inspired by the results A of X and Y, we prove B. And indeed, as today it is Kropotkin's birthday, competition is the law of jungle, but cooperation is the law of civilization. So here is the Schellach's advice, which I've repeated before: never let ideology or aesthetics prevent you from proving a theorem. And here is another anecdote I would like to share because it tells quite a bit. When Hannah Neumann wrote in a book, a chapter in a book on varieties of groups in 1967, where she also studies large numbers, say n, of finiteness conditions and some of their 2 to the n satisfiability problems. In my thesis, I had reduced the problem to the simultaneous satisfiability of 3 such conditions. And at a conference in 1974, I met her husband, Bernhard Neumann, and I asked him about this particular combination of finiteness conditions. And he answered immediately, but this is a stupid question. So, sorry, professor, I mean, I thought quite a bit about it. Why is that a stupid question? So he answered, because we have not the slightest idea how to attack this problem. So the lesson he wanted to teach me is good questions test the limits of existing tools, but they are not just randomly asked because you don't know the answer. The other lesson I learned is that concurrent discoveries are the rule. Our fight for priorities is rarely justified. Scientific discoveries grow in the community like mushrooms. Time and temperature have to be right. Ideas also grow and reach the public when time is right. If an idea is truly formulated by a researcher only, then he is really ahead of his time. One should read a book which is not widely noticed by Wilder, Mathematics as a Cultural System, published in Pergamon Press in 1981. And the lesson is, however, one can be too early and also too late, or one can choose unfortunate terminology. The other one is I read in an interview with Arnold about the question, should we stay at home in the library and think, or should we rather travel a lot to communicate? Should we attend conferences mostly to advertise our own work? And Arnold was asked about the difference between Soviet and Western style research. And the lesson implicitly, but on his answer was, we should serve science more than science should serve our individual purpose. So just going around and ego tripping, I proved, maybe not as good as sitting at home and really digest what you have done. And here is the last quotation from a paper I published during the 85, and when the Star Wars program by Reagan was started, overfunded research is like heroin. It makes one addicted, weakens the mind, and furthers prostitution. Well, I think we can stop here. There are more lessons. You will be able to look at the slides when I eliminate the misprints and give them to the organizers to post them. Thank you very much again.
Thank you very much.